surveys since 2004. As a graduate of TRI's inaugural liner integrity class in 2003, her electrical leak location field experience has exceeded over 100 projects and 110 million square feet. She has written and presented papers to the industry conferences and taught short courses worldwide regarding the technical aspects of liner integrity and leak location surveys. Abigail's expertise is available for providing equipment, field training, classroom education, instructional presentations, engineering consulting, and liner integrity survey execution. She has trained staff in all of TRI's offices locations to provide local assistance on survey projects. So I would like all of us to welcome Abigail and thank her for volunteering her time to conduct this webinar for us. And with that, I'm going to turn it over to Abigail.
Thank you, John, and thank you everyone who has logged on to this. Let me get sorted here to the beginning. Okay, so I put this together as John asked me to put together a series of episodes, and I came up with about 8 of them. So this is the very first one, and I'm really starting at the bottom with the basics. And each episode is going to kind of build on the previous one as we get into more and more advanced topics. I'm going to ask a quick question here. Can everybody hear me okay? Could someone just type in the chat of whether I'm coming across clearly? Okay, good. All right. So I'm going to proceed, and as John said, if you have questions as we go along, I'm mainly going to ignore them until we get to the section breaks, and then I'm going to go back and check to see if there's some outstanding questions for that section. I still will ignore questions if I'm going to cover them in any of the next sections that we have. So this presentation is a summary of all of the different leak location methods. They all work, they just require different site conditions, and they also may be applied in combination depending on what the case may be. So I like to divide these into 2 different groups. There's bare geomembrane methods and covered geomembrane methods. The reason for that is that all of the bare geomembrane methods work, and they work on the same condition, a bare geomembrane. In fact, all of the ASTM methods for these have been updated to include this line that I'm just going to read verbatim from the most recent ASTM revisions. All of the methods are effective at locating leaks in exposed geomembranes. Each method has specific site and labor requirements, survey speeds, advantages, and limitations. A professional specializing in the electrical leak location methods can provide advice on the advantages and disadvantages of each method for a specific project. So these are the kinds of things we're going to be talking about today. What are those survey speeds, labor requirements, and advantages and limitations for each of these methods? The covered geomembrane methods, currently there is only one ASTM for. So it's ASTM D7007, and there's a couple different sections depending on whether the geomembrane is covered with soil or water, and they're slightly different. At the moment, there is a work item in the works for a new ASTM for both soil and water covered geomembranes, and I'll give a really brief description of what we're working on for that work item. The last thing I thought worth mentioning is permanent monitoring systems. Obviously, these are systems that would detect leaks while the containment facility is active. So it's going to be covered by something, soil, water, waste. And so that goes in that category, but we don't have an ASTM for those methods. But I will talk briefly about some of the ways that they do that. So starting with the bare geomembrane methods. Obviously, the geomembrane is bare. It's usually performed as part of the construction quality assurance program. So a newly installed geomembrane that's just going down, just being constructed, and they test it before it's put into service. Or they might test it before some cover material gets placed. We can do this testing on existing older facilities, but it pretty much always has to be cleaned before we go in and test it, because usually there's some kind of debris or maybe sediment built up on the liner, and we really need that liner to be as clean and dry as possible. So I'll start with the arc testing method. This is actually the newest method. The ASTM was created in, I think, 2013 or 14. The geomembrane must be clean and dry, and it has to be underlain by a conductive medium. What do I mean by this? I think the ASTM definition is semi-conductive. It's just conductive enough to conduct electricity. At one point, the ASTM gave the definition of at least 0.5% moisture content in soil, which is true, but only for some types of soil. Sands actually need more like 5 and 6%. So just conductive enough to conduct electricity. For something like a GCL, if it's bone dry, it's not going to conduct electricity. So this method uses a very high voltage. I like to equate it like a lightning bolt out of the sky. It literally just travels through the air with this electrical arc through any leaks in the lining system. So you have this wand that's charged with the high voltage above the geomembrane, and it's grounded to that conductive layer under the geomembrane. And if there's a hole, you get a little electrical arc, and you can actually hear the zipping of the arc. And the equipment also produces an audible alarm. So this is what one version of the equipment looks like. And this is the perfect application for this kind of technology, because this is a geomembrane-lined dam. So you can see if we use some of the water-based methods and we squirted water at the wall to be able to detect the leaks, the water would just run off the surface and fall into the water in the ground below, so it would actually ground out our survey. So this equipment in this photo is grounded to the concrete structure below the facing of the dam. It's just tied around a bolt and then taped. And so if there's any leaks in this geomembrane facing, you'll get that electrical arc right through the geomembrane. The big advantage is it does not require the application of a conductive medium. What I mean by that is you don't need to squirt water at the geomembrane. The testing can perform right up to any grounded objects, and when you're applying water to the geomembrane, it can get kind of messy, and it's very hard to get close to any grounded objects in the survey area. This method is extremely sensitive. It will find basically any hole in the lining system. I wanted to mention that the ASTM requires all of these methods to only demonstrate that they can find a 1 millimeter diameter leak in the liner, which is somewhat difficult to find if you're applying water, because the water has to travel through the hole. But with the high voltage, the hole literally only has to be the diameter of an electron. It can be so incredibly small. So this method is very easy to perform. It's pretty much a point and click. Once the instrument is set up, you just scan the surface, and there's a very undeniable alarm when you actually find a hole. And you can visually see the arc and exactly where that arc is going. So it's very easy to pinpoint where exactly that hole is, even if you can't see it. One of the limitations is that the electrical arc will only travel so far, and that is a function of how humid the air is. I've seen arcs travel through about 1 inch of air, no problem. I've seen arcs travel through geocomposite, no problem. But if you get a gap that's larger than that, it may not sound the alarm. So that means that it's not going to work very well if you have a hole at the peak of a wrinkle and the distance traveled between the top of the liner and the conductive subgrade is more than about 1 inch. It also doesn't work well in the presence of water. What do I mean by that? Is that if you have pools of water, usually the equipment will give you a false positive, and it's hard to distinguish between that and a hole somewhere in the water. Also, in my personal experience, it sometimes works on patches and sometimes doesn't. I'm told by the manufacturers of this equipment that if you allow time for moisture to build up under the liner, that it will work on a patch. And I've seen that because I actually installed a hole on a patch, and when the patch was new, it wouldn't detect the hole. And then I waited a year, came back, and it gave me a positive leak signal on that patch because it took a while for the moisture to kind of gather up under the lining system. So yes, it works. No, not absolutely all the time. So that's something that needs to be addressed. The spark testing method is also a high voltage testing method. The spark testing method was developed in tandem with the conductive back geomembrane product. I'm going to talk a little bit more about the conductive back geomembrane product in a couple of slides. But just know that spark testing method goes hand in hand with the conductive back geomembrane product. You have to have that product in order to do this particular test according to this particular ASTM. It's really important for all of the high voltage testing methods that the geomembrane is clean and dry. Dry is more important than clean, actually. The voltage that we run is, it can go up to 35,000 volts, but not always, not usually. Usually we get false positives when we get that high in the voltage range. So the way the spark testing method equipment is set up is a little bit different from the arc testing method. Rather than connecting directly to the conductive layer underneath, it actually uses a capacitance technique to induce the voltage across the geomembrane using a neoprene pad. And I'll just go right to the picture of that. So here is the neoprene pad that you drag around with the equipment. So you can only test the panel that you're standing on, or the panel that this conductive pad is sitting on. So that makes it a little bit difficult to test something like a very small patch, because you have to have that pad over the liner that you're testing. So this method is assuming that each panel is kind of floating, if you will. It doesn't have to be connected to any of the other panels because you're testing the panel that you're putting the apparatus on. So the advantages are similar to the arc testing. Does not require the application of a conductive medium. It can be performed up to any grounded objects. The geomembrane-lined area does not have to be complete because with the water-based methods, you're putting water on the liner and it will flow to the low spot, and it cannot flow out of the area that you're testing, or else it'll ground out. So it really goes hand in hand with installation of the liner, which is why most of the time this method is performed by installers. Also just as extremely sensitive as the arc tester. And the biggest advantage of this method is simply because it requires that conductive back geomembrane product. The conductive back geomembrane product will enable leak detection on wrinkles. So it doesn't matter how close that geomembrane is to your subgrade, because the conductive medium that you're using for leak detection is an intimate contact on the bottom side of that product. This method also does not work well in the presence of water. It requires the conductive back geomembrane product. And the other issue with this method is that when you have these conductive back geomembrane panels welded together, the fusion weld does not always break the conductive backing of the product. And therefore, you might get false positive leak signals when you get too close to that fusion welded overlap. So why don't we talk about that conductive back geomembrane product? This photo right here is just illustrating the extreme sensitivity of this method. This photo shows a little tiny knife slice, which you probably can't even barely see. It's about maybe 1/8 of an inch in length, and it's a knife slice. And the reason I was so impressed with this hole is that I know from experience that you'd never find that with the water-based methods. So, so the conductive back geomembrane product, if you don't install it in such a way to isolate those fusion welded seams, you can't test all the way up to the seam. You have to stay about, see, the ESTM says 100 millimeters away from the seam. So A method of installing this conductive back product in order to enable other leak location methods and in order to avoid the false positives on the overlap is something that we finally gave a definition to this past year. So we're calling it electrically isolated conductive back geomembrane installation. And all that means is that it's an installation of the typical conductive back geomembrane product that achieves two things. One, a continuously conductive surface on the bottom layer. Second thing, continuously insulating layer on the top of the geomembrane. So, and these two layers do not come into contact with each other unless there's a leak. So what this does is it prevents the false positive on the overlaps, and it also enables all of the other leak location methods that we're talking about today. So I'm just going to read a sentence from the most recent revisions of the spark testing method. It says, electrical leak location methods, in addition to the spark testing method, may be used on electrically isolated conductive back geomembrane installations. So the only reason I'm mentioning this now is that the conductive back geomembrane product has always been so intimately linked with the spark testing method that it's really hard to separate the two. So I kind of have to talk about both at the same time. So any questions about that, just type them into the chat window, and I will cover it after we finish with this section on exposed geomembrane testing. So moving on to the water-based exposed geomembrane test methods. The first one I'm going to talk about is the water puddle method, ESTM D7002. It requires a water source. So you take the water and you apply it over the geomembrane, and you're grounded to the conductive layer underneath the geomembrane, whether it be soil or GCL. If you installed that conductive back geomembrane product, you can ground to that as long as it's installed to be electrically isolated. It uses a very low DC voltage, 27 to 32 volts about, and that charged water is just sprayed systematically over the geomembrane, usually using a roller type system. And when you come across a leak, it gives a beeping tone to the operator. As long as that water is physically able to move through the leak, it'll give you that leak signal. So this is what that looks like. This is a double wide, it's about 2 meters wide roller, and the water squirts out ahead of that roller. The roller is made of like a squeegee, almost like a sponge type material. So it kind of fills up with water, and as it rolls over the hole, it sort of squeezes the water into the hole. So what makes this method really nice is that it's very fast and it can be used in wet or dirty conditions. So I really like this method, especially for the floor of any installed facilities, because if you have wrinkles or other things, you can actually water down the wrinkle really well and then stomp on the wrinkle, and actually the water plus the added pressure is what gives you that leak location even in the presence of like dirt and wrinkles. Let me go back to the side for a second. If you notice in this photo, there's like a brown line kind of on the horizon. This impoundment had all kinds of sediment build up. In fact, it was probably about 6 inches thick in the deepest part of the sand. And we had no problem doing the water puddle method over huge areas of sand. In fact, I found one leak under about 6 inches of sand because that sand, as long as it's touching a hole, once you get close to the sand and hit it with the water puddle equipment, it will alert you that there's a hole somewhere in that sand covered area. And that's something that the ARP testing method will not do. So really good for poor, wet, and dirty site conditions. If it recently rained the site and there's puddles here and there, you can still perform this method. It does not work as well when you have slopes. So anything more extreme than 3 to 1 is usually my personal limit. Anything like 2.5 to 1 or steeper, I like to use high voltage methods, because when you apply water to those slopes, it really just wants to flow off the surface. It does not want to go through holes in the letting system. And I've used these methods in tandem, trying to find holes on slopes and walls, and the high voltage methods always work better for that. One of the other downsides is that you do have additional labor requirements for helping convey the water throughout the sites and having somebody to pull the hoses along. Usually you need 2 laborers per hose plus the water truck sitting around all day. But it's a very fast method. It covers about 4 to 6 acres per day, as opposed to something like the arc tester, which is like 1 to 2 acres per day. So moving on to the water lens method, this method is exactly the same as the water puddle. It's just a different way of applying the water. So with the water puddle method, we have that fancy roller contraption that really efficiently distributes the water over a wide area. But there's a lot of little moving parts, and the structures are all like made. Each part is made by hand from a machinist, so it's a very expensive instrument. The water lens method, the beauty of it is it's literally just a nozzle on the end of a hose. So it's a very simple instrument, but it's applied in the exact same way as the water puddle. So you need the water source. You have to have the geomembrane underlain by a conductive layer. Use the same DC voltage, use the same voltage source, use the same meter as the water puddle, and your equipment gives you a beep when you come across a hole. This is a photo Ian Peggs provided me with years ago, because back in the day, before we had the high voltage testing methods, this was the method of choice for slopes. So, this encouraged the water to squirt through any holes when you had a slope situation where puddled water or ponding water would just kind of slide off the surface. But this method is pretty much the same speed as an arc tester, so it's quite slow, relatively speaking. And now that we do have the high voltage testing methods, it doesn't provide much of a benefit over any of the other methods, really, except for the fact that it's simple testing apparatus. So it's a fairly cheap equipment to put together and fairly easy to apply as well. It is also very tolerant of wet and dirty conditions, just like the water puddle, and has the same requirements for the water truck and the laborers. So it looks like I don't have any questions about the bare geomembrane methods yet. So I will move on to the covered geomembrane methods. So for the most part, these methods are performed on cover material after it goes protective or ballast material over the geomembrane as part of new construction. You can also use this method on existing facilities, but they need to satisfy the same isolation requirements that I'm going to be talking to you about. So the material covering the geomembrane has to be isolated from the material underneath the geomembrane everywhere except for where there might be a hole. And so the entire perimeter has to be isolated. And also any features like inlet pipes or anything going through, any penetrations going through the geomembrane have to be isolated. So plastic penetrations are fine, metal penetrations are an issue. So I'm going to first talk about the soil covered ASTM. The soil, in quotes, can be any conductive or any quasi-conductive material. So this includes gravel, sand, clay, and even concrete. Concrete is actually very conductive and provides really good contact. We usually get really nice leak detection sensitivity with concrete covered geomembranes. The material over the geomembrane has to be conductive, so sometimes it needs watering. Material underneath the geomembrane has to be conductive. And I mentioned that isolation. This isolation is the most important aspect of the sensitivity of the methods, because The current is always going to follow the path of least resistance. If you don't remember anything else about what I teach you today, remember that the current travels the path of least resistance. So if the entire geomembrane is covered with conductive material, and it's grounded to the material underneath it, it will find the easiest route out. So if there's an access road in place that they use to place material, it will follow the access road. If there's an access road in place, it simulates a leak that's the size of the cross section of the access road. So it's not going to go through a 1/4 inch leak in the liner when it can go through that access road. So for this method, we need more voltage simply because we have more resistance in our circuit. And so we're inserting the current injector into the material, and the material might be soil with a 2% moisture content, let's say. And so the current path, it becomes much more difficult for it to go from the current injector to the ground if it has to travel through, thousands of feet of soil. So we use up to about 500 volts. It varies site by site. Most commonly, we run about 200 to 350 volts. But it's not the voltage that's important, but the current. So people always ask me, safety-wise on site, well, how many voltages are you running? Well, that's not really the issue. It's what the amperage level is. And so we use 290 milliamps as a limit, because 300 to 500 milliamps is where it becomes a safety issue, a human safety issue. So I mentioned we put the current injector in the material above the geomembrane. We ground our current source to the conductive layer under the geomembrane. And then we take measurements of voltage in a grid pattern. So let me just go to a visual here. We are basically walking back and forth in the grid pattern throughout the survey area, measuring voltage. So what are we looking for? Well, the entire area is charged with a certain level of voltage, and there's going to be current escaping through holes. And so we're actually scanning the entire area looking for voltage drop locations, where all of a sudden the voltage drops because the current is escaping through a hole in the geomembrane. So it's an indirect way of figuring out where the current is flowing, whereas the bare geomembrane methods are very direct. If you have current flow, you have a hole. If you don't have current flow, you don't have a hole. It's very linear. With the dipole method, you always have current flow. There's always current going somewhere. So we're trying to figure out where it's going by creating an entire map. I'll show you what that map looks like in a couple of slides. So the greatest thing about this soil covered method is that we can detect the damage that's caused during that cover material placement. And it's the only thing that's going to allow you to see that. This method can be extremely sensitive. I've found pinholes with this method, but only if site conditions are good, mostly meaning that the isolation is good. And the only place for current to flow is through those holes. The other thing that's really great about this method is that you can document the entire process with the voltage map. I wish I could figure out how to do that with the bare geomembrane methods, but it just doesn't work like that. So this way, it's like a snapshot in time of what the entire site is doing electrically. And that's an incredibly valuable quality control document you can give to an owner and show them basically scientific proof that you do or don't have leaks in your facility. This method you can perform, usually it's performed right before this facility is complete, before putting it into service, but you can also do it after the fact, as long as you can attain that isolation. It's very rapid when you use the GPS-based data acquisition system. Not everyone uses this. Some people require string lines placed throughout the survey area because they don't have the GPS-guided equipment, and that survey rate is probably up to about 4 acres per day. But with the double dipole and the GPS-based system, at least 8 acres a day is pretty much what we plan on. So the thing about this method is that we will not detect holes if they don't have good contact. So, some people think a hole is a hole is a hole. Well, not necessarily. We're not going to detect a hole that's not leaking per se. If you don't have the cover material is not touching the subgrade through a hole, like let's say there's a bubble in the subgrade, you have a cavity of air, and the cover material is not actually touching the subgrade material, we're not going to detect that leak. If you add water to that same situation and flood that little cavity with water, then we will detect that leak. So the current needs a medium to travel through in order for leak detection. So this method usually requires some amount of site preparation. Usually the contractor is advised on how the site needs to be prepared before you come to site and do the testing. Sometimes it doesn't change the design at all, and it's just business as usual, and we can just come in. But it's highly advisable to plan in advance, because if you come in after the fact and tell them that they need isolation trenches, they'll have to dig them through the cover material, and they could create damage doing that. The sensitivity of this method is typically very reliable to be able to find easily a 1/4 inch hole that's 6.4 millimeters in diameter, very easily find that size leak. But it's highly dependent on site conditions. You can come into a site and easily find that hole on day one, and then it rains overnight and it fills the perimeter up with water, and all of a sudden you have current flowing out the edges, and the next day you come and you can't see that 1/4 inch diameter leak. And sometimes we have to wait until that perimeter isolation actually dries out. So this is what I'm talking about with the perimeter isolation trench. So this particular photo on the left side, that's my survey area, and on the right side, that's just like a perimeter berm there. But you can see the black line of geosynthetics there in between the two materials. So ideally, you want to be able to see the geomembrane there. Very, very often, the geotextile is already in place. That's fine as long as the geotextile is not wet. So like I said, it'll work in dry conditions, but if it rains and the geotextile or geocomposite fills with water, then you lose your site isolation. With gravel and sometimes sand cover materials, we often have to water directly ahead of a survey. Usually we don't need it. I say usually because I perform most of my surveys on the East Coast. I remember on the West Coast, when I did surveys out there, we had to water all the time. So it really is a function of climate, and sometimes you just need to water the surface a little bit because the surface gets desiccated and you're unable to actually get a reading directly on the surface. Regardless, there needs to be some amount of moisture in that entire layer of cover material because the electricity needs to be able to flow through it. So this is what the voltage map looks like that I told you about. So let me just quickly teach you how to read these things. So we have the current injector right here, and this is where the current is coming into the pad. And we're making these voltage measurements with a dipole. So it's always going to be the differential of the front foot minus the back foot in the voltage. So if you're walking toward the current injector with the dipole, everything's going to be positive. In these maps, what I do is I make all positive readings be green or yellow, and all negative readings go from red to blue. And so as you walk, this map was created by walking back and forth as my cursor shows. So you're going forward, backwards, forward, backwards. So as you walk past the current injector, you get negative readings. And so when you're looking for leaks in the data, you're looking for the exact opposite of the current injector. So in the survey area, it causes everything south of the current injector to be positive, everything north of the current injector to be negative. So it has a negative on top, positive on the bottom. Leaks are exactly the opposite. They tend to look like little butterfly shapes. So it's a little blob of positive on the top and a little blob of negative on the bottom. This photo is a little bit hard to see the contours. They're a little bit blurry, but you basically see a bubble, two mirrored bubbles along the direction of the dipole. Positive, negative polarity, that's the opposite of the current injector. So there's two holes in this survey area, one here, and you're looking for that double bubble. Looks like I have a question that came up. When connected to an existing landfill cell, how do you isolate the cover soil from the underlying conductive layer? To leave the stone connection until after the test completed? Yes. So even along the tie-in, I like the landfill to look like this. So you do your geosynthetics tie-in, and then usually, you can actually see it here, they usually leave like a windrow of cover material along that edge. So after we do the testing, you could just push that material into that isolation trench when you're done. Some people get really crazy about it and they want us to like arc test this strip of geomembrane to make sure there's no holes in there before we cover it, and that's fine, but usually people just feel comfortable that there's no leaks there and they carefully push the material in. I think it's a good idea actually to arc test these especially if it's along a tie-in, because I've found plenty of holes on the extrusion weld, especially if the tie-in is extrusion welded. So, all right. So the water-covered ASTM is a different section of the same ASTM number, and the principle is all entirely the same. But there's still a couple of things that are different for the ASTM for water-covered versus soil-covered. One thing that I've learned throughout the years, yes, water can be any solution, including brine, but all of the electrodes that you use in that solution have to be non-reactive with the solution. So, you know, some stainless steels are going to react with salts, so you need to figure out an electrode that's not going to react with whatever that material is. Every chemical reaction is just an exchange of electrons, right? An exchange of electrons is a differential in voltage, so it will throw off your voltage measurements. The solution, it's when you have a more highly conductive material over the geomembrane, the isolation becomes even more important. I've had sites that don't have the isolation trench at all, but we were still able to perform a sensitive survey because the material over the geomembrane was so dry and non-conductive. We could actually selectively water the survey area and it didn't compromise the sensitivity. But when you have solution covering the geomembrane, it's so conductive, even if it's just water and not necessarily a brine. If you have one metal pipe going into that water, I doubt it will work using the ASTM method. And then also, because that material is so conductive, you don't have to use as much voltage because the material is so conductive, it doesn't have as tortuous a path. It's easier for the electricity to flow. So we usually use up to about 75 volts, but again, it's dependent on the current, and the limit is always human safety. The limit is always 290 milliamps. This is something that people don't really talk about a lot, but I like to be very vocal about it because no matter what, no matter who's doing your survey, you should always ask them as part of your safety meeting before you even start the project, what's the maximum current you're going to pump into this pad? Because if they're going to go over 290 milliamps, all of a sudden it becomes a safety issue, especially with solution. So this is the same principle. You put the current injector in the liquid above the liner. You take measurements of voltage in a grid pattern. However, the ASTM for water-covered geomembrane does not require the data recording. Instead, it's a lot like the water-based bare geomembrane methods, where something just happened to my screen. What happened to my screen? I fixed it. There we go. So what's going on with my screen? Somebody is messing with my interface. The attendee list keeps covering my pictures. There's the chat. Okay.
You back?
Right now it looks okay. Okay, so if anyone's having trouble hearing or seeing anything, go ahead and put it in the chat. So the water cover dipole method looks just like the photo that you see here. It's one guy walking back and forth in the water with a little detector that beeps when there's a hole. Now, I will tell you that this detector has a very wide range of adjustments. So you can adjust it so that it's barely sensitive enough to see a hole, and you can adjust it so that it beeps no matter what. So it's really susceptible to user error, even though when you have it keyed in just right, it's very difficult to ignore this audible signal that you get when you're on a leak. So the reasoning behind the ASTM of requiring the data recording for the soil but not for the water is that the creator of the ASTM said, well, you can't really ignore an alarm beeping in your ear, which is true, but in my mind, having a voltage map of the entire site is so much more valuable than trusting a guy to walk around back and forth and hear the beep every time, and for the equipment to be exactly adjusted right and be able to say, okay, I cover the entire area and this is where your leaks are. You have no document that shows that at all if you just follow the ASTM. So the advantage of this method is that you can perform it on flooded areas, especially if the pond's in service. One thing I like about it is that, you know, if I'm doing a survey of a landfill and it rains a lot and the sump gets flooded, then I can just go in and do the water covered, you know, survey in the water itself. So this sensitive is just naturally more sensitive than the soil covered because you're actually forcing water through holes. So if there's a hole in the liner, chances are it's going to be leaking when you perform this method. So it's extremely sensitive in that way, that it forces water through the holes, even if there's a tortuous path. So I mentioned that it's very susceptible to poor site conditions, and you really have to think about any kind of inlet or outlet structures and penetrations. If the outlet for your pond is a concrete outlet that's installed there, you're not going to be able to perform this method there. So one of the requirements for the new ASTM that we're working on is that you actually have to record the data when you're doing a water covered survey. So I personally don't really like the reliance on the audible signals. So the preparation for water covered sites is really the same as the soil covered. So this is a pond that we surveyed where you see there's this it's actually a pump connected to the sleeve, and made sure the pump was totally disconnected, and there was a muddy strip of just sediment around the perimeter, so we just worked on cleaning all that up. We put a dry wooden block kind of propping up that sleeve that had liquid in it, and now you also want to make sure that the sleeve is evacuated of liquid. Now, is this a perfect isolation? No, it's not. In fact, this will probably come up and show as a leak signal. But by reducing the contact, we're trying to prevent the sensitivity of the survey from being compromised. So we're doing our best to isolate the material above the liner. The reality is it's pretty much never perfect isolation. John had mentioned I've surveyed over 100 sites, and the vast majority are dipole, and I've only had a couple of sites with perfect isolation. So, I mean, the ideal is one thing and the reality is another thing, but you always want to shoot for the ideal whenever practical. So, another thing about the water covered dipole method is that it's very difficult to get a precise leak location when you have a filled pond. So, using the dipole method in a filled pond, you actually attach a dipole to a cable, and you pull the dipole back and forth across the pond. Now, the only way you know where that dipole is at any given time is that you have length markers on the cable itself. So you know that you can say, okay, I got a leak signal maybe 50 feet away from where I'm standing on the bank, And then next thing you know, you have orange flags on the bank saying, okay, signal is approximately 50 feet out from this flag. And the method is very sensitive. It can detect a pinhole. So, you go through the trouble of draining the pond and cleaning the water, and you go out there to inspect where that hole is. And more likely than not, you won't even be able to visually see it because it's such a small hole. Sometimes it's obvious, but sometimes it's not. And the other problem with this is that if you're not recording the data, you're only listening for beeping, then you might be able to see a given leak in multiple passes. So see in this photo, I have 3 different flags set there because I got a signal on this line and this line and this line, but it's impossible to know without data recording where the actual peak of that signal is coming from. So the certainty of where exactly that signal is coming from is just really large. Like I would say in excess of 10 feet easily for these completely filled ponds. I still like the dipole method for filled ponds, but you have to specify data recording and also precision in the location of where they're requiring the data. So they would have to stake out the entire pond, keep track of where exactly they are when they're recording the data, and then they can produce a map that's fairly accurate. And they can also give you the level of certainty or uncertainty as far as the actual leak location. So getting back to some of the issues with the ASTM that I've mentioned, we are working on a new work item that's called Electrical Methods for Eliminating Leaks in Installed Geomembranes. I realize this is a very ambitious title, but if you were to actually follow all the protocol and you could actually get the perfect site isolation, you will be able to tell with complete, I say complete with a grain of salt because as an engineer, I never say anything is 100%, but 99% certainty that if there's a leak in there, you will find it. So it actually requires the geomembrane to be in an active leaking situation. So it requires the proper site preparation. And if for some practical reason you can't get the perfect site isolation, you have to document where the site isolation was compromised. And more likely than not, that will show up on the data map. It requires the electrical map. In my experience, I've been doing electrical mapping for, 8 years or so, and I surveyed for a long time before that. So I started with the very basic methods of finding leaks just as you go, and then we went to graphical data methods, and then we went to the GPS mapping. And I can tell you without a doubt, there are such tiny, tiny holes that I have found dozens and dozens of that I never would have found if I hadn't done the GPS-based mapping. Because in the map, we can see signals that are so incredibly small that you won't see them when you're just looking at the voltage because it doesn't give you a strong polarity sign change. You can only see them because you know the pattern that a leak is supposed to make in the data. And it will give you that same butterfly-shaped pattern, it just won't be a very big magnitude. So I myself am not 100% sure that everything was done correctly unless I can review the data map. And if the site conditions are not good, the map will actually show you that and show you where the site conditions are not good. So this new ASTM is going to provide a method to actually document a zero leak condition. And in order to do that, you have to have zero leaks, right? So you might need to have multiple surveys done. So I would say it's not very often that I go to a site and not find a leak at all. Usually I find at least 1 or 2. There are exceptions, but if you go into a site and you survey it and there's a leak, the voltage looks very, very different than if you go into a site and there's no leak at all. Because if there's no leak at all, where is the current flowing? Well, it's really not. It's not flowing. There's a very, very tiny, tiny amount, 0.000 milliamps going through an intact geomembrane. But the magnitude difference when you introduce even the tiniest of holes in the geomembrane is a huge difference. So you can actually show what the mapping looks like with a leak, and if there's no leaks in the facility, show how the facility is behaving, and we'll tell you beyond a shadow of a doubt, if you're forcing that facility to leak, like spraying it with water for a few days before you do the testing, you have a 99% certainty that you can eliminate any leaks in that facility. So I'm going to briefly mention permanent monitoring systems. I am not an expert in these systems. If you want to know more about this, I can refer you to other companies who do this all the time. But I don't personally do a lot of these, mostly because they're not very common, especially in the US, mainly because of the cost. But if you have something like, there's some nuclear facilities in the US where they have to do this monitoring all the time. They do this monitoring more in Europe, probably because there's just the population density is so great that you just really don't want these facilities leaking. So you install this as part of the construction phase. Some newer technologies will let you do it after the fact, but it will allow you to monitor for leaks for the life of the containment facilities. So one type is a wire grid that's installed. Usually it's a double contained facility double line facility, because whatever it is that they're containing, they really, really don't want it to get out. So they install this electrode grid above the secondary and under the primary. The detection accuracy is going to depend on the grid spacing. I think of this as like an inverted dipole survey. Let me just go to this next slide here. So you have all these wires laid out above the secondary, and it behaves just like a bunch of dipole feet location, where you're measuring voltage potential in this grid pattern. So that's why the detection accuracy depends on the spacing. The system, to keep in mind, the system will only function for as long as the components last. So these installations are very expensive, mostly because the components are extremely expensive. I know one company who has worked on these installations said they were developing their electrodes for like 8 to 10 years of R&D. So some people who will install lesser systems might not use those fancy probes, and your system might actually not last for as long as the containment facility lasts for. So that's not what you want. So it's not popular, mostly because of the cost. Many, many, many times more expensive than the mobile ELL methods. This newer technology I referred to is from, I think I just got this off of GSC literature with a company that they're partnering with to do permanent installation systems. So this was the density that they gave of the sensors installed above the geomembrane, not below it, but above it, so they can actually go into existing facilities and install this on top of it. However, there's no ASTM standards for these. They're very specific to the company installing these systems. So this is kind of the old school method of installing these. And this particular guy, I'm told, travels all over the world and keeps track of all these individual wires that come out from the leak detection layer. So better than me, is all I gotta say. So this is a photo from the newer technology where they can install these sensors above the geomembrane, and they're actually welded to the geomembrane. And I believe they work on some kind of triangulation type algorithm where they can place fewer modules, and the modules kind of communicate with each other, and they can tell by distance of the signal travel between the sensors where exactly the leak is. So here's this test facility they installed where they're figuring out where exactly the leak was in this comment. So moving, let me check for, yeah, Texplore is the Austrian, I don't know if they're Austrian or German company who does this. So method selection. So you really need to consider what an acceptable level of leakage is for your site. It's not like one method is the answer, but as a general rule of thumb, specifying the bare geomembrane survey before the cover material placement and then the cover material or cover geomembrane survey after material placement is going to give you a very high level of integrity. However, you have to remember that holes on wrinkles result in 100 to 1,000 times more leakage than holes in intimate contact with the subgrade. And most of the ELL methods that we have talked about will not detect a hole on a wrinkle. So this is a compound problem. So it doesn't have one fix. You can't just throw leak location at a project, and you can't just throw wrinkle management at a project. You have to do both. So ELL in tandem with wrinkle reduction or elimination is required for the highest level of containment. And you also have to ask yourself, is what I'm working on so important that we need to know in the future whether it's leaking? If so, consider the permanent monitoring, or you can also have periodic monitoring with the mobile methods that we've talked about today. I've heard people talk about every 5 years performing a survey, or every 1 year, every year as part of the annual upkeep of the facility performing a survey. So this is kind of an example for a soil covered impoundment. So if you're specifying a method for soil covered, the very minimum is you have to specify a covered geomembrane method. You have to, because the most significant leaks are going to be caused while that cover material is being placed. You want to make sure you do not miss those leaks. Construction damage, like insulation damage, like knife slices and pinholes, that's one thing. But a dozer rip, you don't want to miss that. So if you really are serious about leakage, you do want to specify the bare geomembrane before the cover material placement and then covered after. But even better, have a wrinkle management program. The best would be wrinkle elimination. Now, I know that sounds crazy in our world, so I came up with what I call virtual wrinkle elimination. I'll explain what that is in a second. But if you can eliminate the wrinkles, actually or virtually, plus do a bare geomembrane survey, plus do a covered geomembrane survey, that's the belt and suspenders approach to managing leakage. So wrinkle management, what am I talking about? Well, you can specify that the liner can't be covered during certain times of the day in hot climates. You can specify white geomembrane. I believe Richard Brockman recently worked on a bunch of research that actually quantifies how much the white geomembrane is reducing wrinkles. So you can actually do it as a percentage of the lined area that's no longer covered in wrinkles by using the white geomembrane. And then what I call virtual wrinkle elimination, it's not actual wrinkle elimination, but you can use that conducted back geomembrane product. You can also flood the geomembrane. I've had problematic projects where the dipole survey was not working to pick up leaks in soil covered areas, so we had them flood it with 2 or 3 inches, flood the leak detection layer, and we found a bunch of pinhole leaks. And so that's the other way. Even if you have wrinkles, you're enabling the leak location methods to work regardless of the wrinkles being there. So this is how that works. When you have that conductive back geomembrane product, you have a gap here where the electricity cannot touch the subgrade, and it doesn't matter because it can touch that thin layer of conductive backing. Or if you fill this thing with water, the water will conduct through that bubble between the geomembrane and the subgrade. So you can get really fancy about it, and you can take an approach of, what is the probability of exceeding some leakage? Because a lot of this is guesswork. People guess how many leaks per acre. People guess what the size is of those leaks. But we don't really know. It's all guesswork. And so even if you do your best guesswork, you still might get a range of leakage. And so what you can do is you can actually use a probability equation to figure out what's the likelihood that I'm going to exceed this leakage rate. And then you can decide what the acceptable level of risk is. I'm not going to get too into this because we've already gone a little bit over an hour, but you have the source on the bottom right-hand corner here of where I got this equation. And you basically choose the equation which best suits your liner cross-section. Do you have free flow Do you have intimate contact, or do you have wrinkles? So those are the 3 different equations you would use for those scenarios. You can assume some number of leaks per hectare, and then you can apply the appropriate reduction of leaks if you were to perform ELL methods. So you have different leak sizes that you're going to find through those methods. So you assume that some of those leaks are going to be reduced. And then you use this equation to find the probability of exceeding some leakage rate, X, given that you've calculated what the average should be with the mean. Okay, so I know that sounds abstract, and it sounds like that can't possibly mirror what happens in real life, but it actually does, because that equation came from actual data that was collected from 122 different landfill cells. I went through leakage data from the landfills in upstate New York back in 2012, it was. And this graph right here shows the probability function with the blue diamonds. So this is what that function kicks out when you tell it, okay, this is the leakage rate. I want a probability of exceeding this leakage rate if I think this is what my average leakage is going to be based on the technologies that I apply. And so these little red boxes are actual data from landfills in upstate New York. So these were the actual percent of landfills that exceeded the given leakage rate compared with the theoretical. So it fits the curve very well. So it is a very useful tool for dealing with all of these guesses that we're making. Every time we're trying to figure out how much our facility is going to leak, we're making guesses. So we can make educated guesses, then we can come up with a probability of exceeding some leakage rate, and then we could decide whether we find that level of risk acceptable. So I'm just going to quickly go through some case studies where multiple methods were required. I'm personally a really big fan of design engineers not specifying what method they want the leak location contractor to use, because hopefully the leak location contractor will use the best one for the conditions. This was a landfill that had not been put into service yet, but they knew it was leaking because they got a bunch of rainfall and their geomembrane became a waterbed. So somehow water was getting through the liner and lifting up the liner, and it was a waterbed in spots. So the condition of this landfill when I was hired to go out and do the testing was the geocomposite was all completely installed and wet, and then they had the sump filled with water, and then they had a whole bunch of sediment. It was very clayey sediment on the bottom, I would say 1/5 of the landfill. So I actually used 3 different methods on this. I actually had them peel back the geocomposite. You could see they're starting it in the corner. They peeled back the geocomposite completely, and I did an arc testing method on the entire upper end. Why did I use the water puddle method instead of the arc testing? Well, because I thought there might be a hole in here where the water is sitting, and if I had applied water using the water puddle up top, it would have just flowed to the sump where there could be a hole, and it would ground out my whole survey. So I would be hearing leaks everywhere I walked. So I wanted to do all the upslope with the arc testing method. I found 3, maybe 4 holes using the arc testing method up there. And then I came down to the sump and I did the water dipole method. I walked back and forth in the sump. I found 1 hole using the water dipole method right on the corner. I think it was there. And then I did the soil covered dipole method everywhere that you see covered with mud. In fact, I had them put even more mud on that area to make kind of a homogeneous, muddy area. And we found the biggest hole in the soil covered area right at the edge of the sump right about there. So we used 3 different methods. Every method found a leak, and every method was absolutely crucial. So if I had tried to fit this project into one box of one method, it would not have been very successful. So this is another project where you have a tank that's double lined and they know it's leaking. Well, it's double lined, meaning they have a geomembrane as the primary and they actually use concrete as a secondary. So fortunately for this project. Thank goodness for the person who designed this tank. These structures, these ladders that you see here, the first time I saw this tank, I said, no way. And they said, don't worry, they're fiberglass stairways. They're actually fiberglass, so you can actually perform a dipole method survey of the bottom, and this will not conduct electricity out of the cell. So this particular tank, you could do water dipole on the bottom, detect leaks through the concrete, and arc testing on the sides, on the walls there. Those are the two perfect methods for these conditions. Because the bottom of this this tank was actually covered in concrete, so the wall cross section was just geomembrane on concrete. The bottom of the tank was concrete, geomembrane concrete. So you had to do a dipole method over the concrete. In fact, you could see my dipole equipment sitting here in the water there below the stairs. So we have methods available for practically all the geomembrane conditions. Every method has advantages and limitations. People often ask me what the best one is, and there really is no best one. It's just what is the best one for the site conditions, and they can change too. It's really important for designers to be flexible. And this wording at the bottom here, designers should allow for alternate methods when mutually agreeable and warranted by site conditions, logistics, or schedule. That's straight out of the ASTM. Because if, for example, you want to do a bare geomembrane survey and the design engineer says, I want the arc testing method, because I hear the sensitivity is fantastic. So the crew mobilizes, and the night before they do the survey, it rains on the site. Okay, all of a sudden your site is covered in water puddles. It's incredibly hard to sweep off and dry out and get all those puddles away to use the arc testing method. So you can allow them to switch to the water puddle. That's pretty much what you have to do. Usually, even if you have a site that gets rained out like that, you can still do arc testing method on the side slopes, and then you can do water puddle method on the floor. That works really well. So one thing I always want to stress is you need those good site conditions, especially the survey area isolation for the dipole method. It's absolutely essential. There's nothing that I can do on my end when I come in to do a survey. I don't have a magic wand to make the electricity go through only the holes and nowhere else. If I don't have good perimeter isolation, I won't be able to give you a good survey, and that's all there is to it. So the method choice, it really is a function of site conditions and also engineering objectives. So if you're a design engineer, you're very savvy about all the methods, then yeah, you can be pickier about what exact method you want performed, whether you want the bare geomembrane and the dipole method. I'm seeing that more and more, and you know that you're going to get a better product at the end. So with that, it looks like I don't have questions in the box. Somebody ask me a question so that I know there's somebody out there, please. Okay, that's a very, very good question. What is my opinion on ASTM D7909? My opinion is that it has its place, but I will never be a fan of poking in a hole in a perfectly intact lining system. I'm going to give you one example of where I feel like 7909, this is, for those of you who don't know, this is where the CQA agency or the owner or anybody deliberately places a hole in the liner to make sure that the survey is carried out correctly. We're working on a project where we have liner cross section is geomembrane, geocomposite geomembrane, and they flood the geomembrane or geocomposite with water, and the whole thing is covered by gravel. So we're doing a dipole survey, and we're grounded to the water in the leak detection layer. But it's very, very hard to get an even distribution of water in the leak detection layer. So they actually use ASTM D7909 to intentionally place leaks, not to make sure that we're doing it right, I mean that too, but also to make sure that the water distribution in the leak detection layer was thorough. That's a really good reason to do 7909, to deliberately place a leak in the lining system. I understand why people do it, but from my side, when I come in and do a survey, I'm doing everything 100% as well as I can. I'm producing a voltage map, which shows to the owner that I covered the entire area. And I can prove that I did and prove that it's leaking. So in my mind, that's better than poking holes in the liner that is going to result in patching, which is inferior than the original geomembrane, and give you failure points for the future. So my personal opinion of D7909 is much more negative than I think most people's are, but I do understand that owners and CQA folks want to make sure that the survey's working, but I honestly feel like there's a better way to do it. And unfortunately, the better way to do it requires some amount of education. Like they want to, if they want to know if an art testing method is working, you observe it. You understand what's going on. You have a guy watching, making sure that yes, the guy is able to detect leaks. Yes, the guy covered the whole area. To me, that's more comprehensive than just poking a hole and seeing if they find it or not. Because the truth is that sometimes they can poke a hole in, say, an area that is under an overlap flap or something. You know, even though 7909 says that you're not going to find a hole on a wrinkle, most likely, they still, somehow, they always poke a hole in a spot that is either very difficult to find or nearly impossible to find. So sometimes it causes more problems than it solves. And I think just approaching it with trying to make sure that the survey is done correctly in the first place, and especially with the dipole requiring a voltage map as proof, I think that's much more powerful. Now I wish I could unsilence everybody because I don't want to only hear my own viewpoint, but feel free to dispute and comment and discuss in the chat box. Oh, I got one amen, so.
Abigail, this is John.
Okay.
I just, if there's no more questions, we've gone a little bit over, and doesn't appear to be any more questions. I'd like to say thank you on behalf of all the attendees for your time and your expert opinion and knowledge base that you've shared with all of us.
Thank you for allowing me to share my expertise. It's always a pleasure.
I believe that we're all looking forward to your next seven webinars and learning about this field that you participate in and reducing leakage within containment systems. I would also like to encourage everybody to sign up for our next webinar that's going to be presented by Beth Wilbanks on the understanding of MARV, or the minimum average roll value. Beth's been in the industry a long time, working for Tincati, and she brings a lot of knowledge about MARV and what it means, and just clearly defining it and allowing us to use it all in the same manner, which over the years has been a very challenging task. I would also like to promote IGS North America and the webinars that we're presenting. I noticed a number of you that have attended today are not members of IGS, and I would like to encourage you to become members. We've got a very strong webinar content lining up for next year. And as becoming a member, you will get a discounted rate, and you'll get one free webinar. All of our webinars will offer PDHs, so it's an excellent way to pick up very cheap PDHs for the year and improve your geosynthetics knowledge base. That membership can be done through the IGS website at www.igs-na.org. If you have any questions, you're more than welcome to contact any of the board members through the website. And once again, I hope to see you all at Beth Wilbanks' webinar next month.
John, we did
With
have
that,
one question about the handouts for this presentation, and I know that Elizabeth said she was going to put it together. I just want to point out that question there that came through.
okay, we'll
Send
wait
them
for
out
that to
for the
come.
attendee. We'll
Go
send
ahead,
out a
Elizabeth.
follow-up. Sorry, we'll send a follow-up to everybody that registered in the room. Email, a follow-up email, and a PDF version of the slides. So 2 or 3 to a page, I think.
There's our answer. With that, we have one more thing coming in. Thank you. With that, we will conclude. We'll see you next month.
Thank you. Thanks, Abigail.
No problem.